Greetings and welcome to the series of lectures on rational exponents and roots. 6.2 Simplified Form of Radicals. So we're going to be working with the simplified form of radicals, but we do need to talk about some of the properties that we have available to us to be able to get radicals in a simplified form, which I'll tell you about in just a few. So let's talk about the properties first. The first property for radicals is the nth root of AB will equal, excuse me, the nth root of A times the nth root of B. Well, why is this possible? Here's the proof of it. Normally I don't like to show a lot of proofs, but this one was kind of short and sweet and kind of made the point across, I think, a little easier. The nth root of AB will be AB raised to the 1/nth power. Using exponential rules, we can distribute that 1/nth power to both A and B. So now we have A to the 1/nth, B to the 1/nth. But then rewriting it in a radical format will give us the nth root of A times the nth root of B. Property 2 for radicals is when we have the nth root of A over B, that will be the nth root of A all over the nth root of B. And remember, when it's working with fractions, we don't want B to be, the denominator does not want to be 0. Okay. So what's the proof for this one? It's very similar to proof for the first property. So the first thing is to write your exponent as a fraction. So the nth root of A over B will be A to the B raised to the 1/nth power. Then, using our exponential rules, we're going to give that 1/nth power to both the numerator and the denominator. So A to the 1/nth all over B to the 1/nth. But then rewriting it in the radical form will be the nth power of the nth root of A all over the nth root of B. So now what does it mean to be simplified form of a radical expression? If none of the factors of the radicand can be written as powers greater than or equal to the index. We'll talk about that more in a little bit, but let me give you a quick example. So what does that mean? The factors of the radicand, and I'm going to say 2 to the 4th, so the square root of 2 to the 4th. Well, the index here is an implied 2. The power of the radicand is 4. Well, 4 is greater than or equal to 2, therefore none of the factors, this falters, this fails this first test, so we would need to simplify this value first. That's the first rule. There are no fractions under the radical sign, so we don't want anything that looks like 1/3 or the 4th root of 4 over 9. Nothing like that. No fractions underneath the radical sign. The third rule is there's no radical in the denominator. Okay. If we have something that looks like 2 over square root 3, we don't want that. That's not in simplified form. And there's, well, steps that we can do to eliminate the power being larger under the radical symbol, no fractions underneath there, and then also no radicals in the denominator. Now I'm going to show you quite a few examples for more so than I would normally give you examples, but I think by seeing it over and over and over, that will help you understand what it means to be in simplified form for a radical. All right, so let's write the square root of 50 in simplified form. Well, the first thing I do see is it can be written, 50 can be written as 5 times 5 times 2. And 5 times 5 can be written as 5 squared. Okay. Now I have the ability to break this radical up into two separate radicals. That would be the square root of 5 squared times the square root of 2. Now, the square root of 5 is 25, and we do know that the square root of 25 is 5. Okay? So that becomes 5 times the square root of 2, and in simplified form we don't need this marker for multiplication, so we're just going to write it as 5 square roots of 2. Alright, let's see another one. The square root of 450 in simplified form. Now remember, we have 3 criteria for simplified form. One is there's no power underneath the radical symbol that's greater or equal to the index. The index here is a square root, therefore the index is 2. Second one is no fractions. Well, we're not dealing with fractions here, so we don't have to deal with that. And the third one is no radicals in the denominator. Well, we don't have a denominator, so we only have to deal with the first rule. First things first, let's go ahead and break up 450 into its prime components. So let me go ahead and work that out with you. 450, well, I can definitely see that there is a 5 in there. 5 times 90 is 450. Okay. There is a 5 that lives in a 90 as well. So 5 into 90 is 18. Okay. There is a 2 that lives in 18, 2 times 9, and 9 can be broken up as 3 times 3. So 450 can be written as 5 times 5 times 3 times 3 times 2. Okay. But that also could be written as 2 times 5 squared times 3 squared. Okay, so let me get this out of the way so it's just not distracting. In other words, I can break it apart into individual radicals. So square root of 2 times the square root of 5 squared times the square root of 3 squared. That would be the square root of 2 times 5 times 3. And we can do this math of 5 times 3. That's going to be square root of 2 times 15. And then the last step is to really rewrite it in the order that we want it in. We're going to have our coefficient, we're going to have our constant in front, and then our radical in the back. So it's going to be 15 square roots of 2. The previous examples only dealt with numbers, but we will also have variables underneath the radical symbol. And in this case, we want to limit the variables, and we want to say that they are greater than or equal to 0. Okay. So they are non-negative. So let's write this in simplified form. The first thing we'll want to do is we want to break down 48. 48 can be broken down into 2 to the 4th times 3, and then that just gives us times x to the 4th, y cubed. I'm going to break these down a little bit more. Separate them out. Square root of 2 to the 4th times square root of 3 times the square root of x to the 4th times the square root of x cubed. Now, there's a couple ways of doing it. One is now to raise them all to the 1/2 power and use your exponential rules. And I've done that here. Not my favorite route of doing this type of math, but I just want to show it to you that it's possible. So, since the square root is to the power of 1/2, that leaves 2 to the 4th times 1/2, or to raise to the 1/2 power. Square root of 3, I went ahead and left it as is, but I'll change it in a second. X to the 4th to the 1/2 power, and y cubed to the 1/2 power. Right? I'm going to simplify this as much as I can. 4 times 1/2 is 4 over 2. 3 to the 1/2. 4 times 1/2 is 4 over 2. And 3 times 1/2 is 3 over 2. Now, that number, 4 over 2, will reduce down to a power of 2. That 4 over 2 will also reduce down to a 2. And this 3/2, I broke it apart. I broke it apart into 2 over 2 and 1/2. because 2 over 2 will reduce down to 1. So here's what we have so far. 2 squared times 3 to the 1/2 times x squared times y to the 1/2. So rewriting it in radicals will be 4x squared, because 2 times 2 is 4, 4x squared y. Those were all outside the radical, and anything that still has the 1/2 power will stay inside the radical. So 3 and y stay inside. Like I said, it's not my favorite way of doing it, but it is possible to do it with the fraction exponents. Alright, let's work with a little step up, and I'll try to be very clear as to what I'm doing here. The third root of 40x to the 5th b to the 4th. First thing I want to do is I want to break up the 40 into its prime components. And it's 2 cubed times 5. And I left the a and b alone. But here's what I can do. I'm going to break these each apart separately. And I want to write them in powers of the index. See, the index is 3. So if I can write it in powers of 3, this will be helpful. So 2 cubed, well, it is 2 cubed. 5 is only 5 to the 1st, nothing I can do there. A to the 5th, I can write it as a to the 5th will equal a cubed times a squared. Why? Because 3 plus 2 will equal the 5 that I started off with. B to the 4th, I can write it as b cubed times b to the 1st, because 3 plus 1 equals 4. Now, why was this helpful? For every one that matches the index, with every power that matches the index, that will be outside of the radical symbol. So 2 cubed will pop out as a 2, a cubed will pop out as an a, and b cubed will pop out as a b. Therefore, I can write it as 2ab times the cube root of anything that didn't come out. The 5, a squared, and b. That all remains inside. To me, as long as I can match up the power with the index, that is going to be popping out. So let me work through another example, very similar process. The 5th root of 64 x to the 8th, y to the 4th, z to the 11th. Right, so first things first, I'm going to break down the 64. 64 is 2 to the 6th, so now I have the 5th root of 2 to the 6th, x to the 8th, y to the 4th, z to the 11th. I'm going to take each one of these and break it down with the index of a 5. Can I rewrite it with a 5 as its power? 2 to the 6th, I can write it as 2 to the 5th times 2 to the 1st. Because 5 plus 1 equals 6. X to the 8, I can write it as 5 x to the 5th times x cubed, because 5 plus 3 equals 8. Y to the 4th, nope, can't write it in any powers of the 5th. No, not 5 minus 1. That doesn't help me. So I just leave it as y to the 4th. Z to the 11th, I can write as z to the 5th times z to the 5th times z to the 1st, because 5 plus 5 plus 1 will equal 11. Okay. How does that help me? Every power of 5 will come out of the radical. Any power that's not a power of 5 will stay inside the radical. 2 to the 5th comes out, becomes a 2. X to the 5th comes out, becomes a 5, x. Z to the 5th, that's z. Z to the 5th is another z. Z times z is z squared. And everything left inside, 2, x cubed, y to the 4th, z to the 1st. Alright, so let's go back to numbers, leave variables behind for just a moment, and we want to simplify some fractions. Square root of 12 all over 6. Well, square root of 12 is really 2 squared times 3 all over 6. The 2 will pop out because the square root of 2 squared is 2. So that's 2 square roots of 3 over 6, but 2 over 6 can be reduced. We are not going to reduce this 3 inside the radical with the 3 outside. That doesn't work. But the 2 and the 6 can be reduced. 2 goes into 2 once, 2 goes into 6 3 times, therefore it's 1 square root of 3, which is an implied 1 out here, all over 3. Let's look at another one. 5 square roots of 18 over 15. First thing I'm going to do is try and reduce it down as far as I can. So 5 and the 15 can be reduced. 5 goes into 5 once, 5 goes into 15 3 times. So I'm left with the square root of 18 over 3. 18 is 3 squared times 2. Therefore, this 3 squared, well, the square root of 3 squared is 3. So I have 3 square roots of 2 all over 3. 3 goes into 3 once, 3 goes into 3 once, leaving me square root of 2. 6 plus the square root of 8 all over 2. I cannot reduce this 2 and 6 because I have addition. It's just like 6 plus x up here. Because I have addition, I have to simplify the numerator first and then see if I can simplify it with the denominator. So 8 can be written as 2 cubed. So I have 6 plus the square root of 2 cubed all over 2. 2 cubed can be written as 2 square roots of 2 because that's 2 squared times 2. The 2 squared reduces. So I have 6 plus 2 square roots of 2. No, I cannot just cross out these 2 because I have the addition symbol still there. I have to first factor the numerator. Once I factor the numerator, I'll get 2 times 3 plus the square root of 2 all over 2. The 2's will then finally reduce, leaving me 3 plus the square root of 2. Let's try another problem here. Negative 1 plus the square root of 45 over 2. Well, the first thing is negative 1 plus, and I can rewrite this square root of 45 as 3 squared times 5 all over 2. The square root of 3 squared is 3. 3 square roots of 5 all over 2. Is there anything in the numerator that I can factor? No. Therefore, that is my final answer. Try another problem. 12 minus the square root of 12, all divided by 6. Resist the urge to divide everything by 6. It's not quite there yet. We do need to first simplify our radical. 12 minus, and that's going to be 2 squared times 3, because it's 4 times 3, all over 6. The 2 will pop out, giving us 2 square roots of 3 all over 6. Now I need to factor the numerator. 2 is the GCF, 6 minus square roots of 3 all over 6. Now I can reduce. 2 goes into 2 once, and 2 goes into 6 3 times. So my final answer is going to be 6 minus the square root of 3 all over 3. Okay, let's try negative 4 minus the square root of 8 all over 2. First things first, simplify the square root of 8. Square root of 8 is 2 cubed, and therefore it can be rewritten as 2 square roots of 2. That one's pretty common. You'll get that one pretty quickly. You'll probably memorize it pretty quickly, Right? Now, can I factor anything out of the numerator? I can. So I can factor a 2, leaving me negative 2 minus square root of 2 all over 2. Reduce. Therefore, negative 2 minus square root of 2. Let me work through another problem here. I just want to give you enough examples to where you can see the process. Alright, first things first, simplify the radical. 6 minus, and 48 is going to be, well, let's see, 48. There is a 2 in there, 24. There is a 2 in there, 12. There is a 2 in there, 6. And there is a 2 and a 3 in there. Okay, so it's going to be 2 to the 4th times 3, okay, all over 8. Well, let's see. 16 minus, well, 2 to the 4th. 2 2's are going to pop out, so 2 times 2 is a 4. You can also think of it as, what's the square root of 16? Well, the square root of 16 is 4, and that comes out 8. Now we need to factor the numerator. 2 times 3 minus 2 square roots of 3 all over 8. And final step, let's reduce. 2 goes into 2 once, 2 goes into 8 4 times. 3 minus 2 square roots of 3 all over 4. There is our final answer there. In this next set of examples, we're going to have a radical in the denominator, and that is against one of our rules for simplified form, having a radical in the denominator. So we're going to learn how to rationalize the denominator, which just means forcing the radical to go away. Okay. Let's take an example. Let's simplify the square root of 3/4. Well, the first step is I can rewrite it as the square root of 3 all over the square root of 4. Okay. That means there is a radical in the denominator, and that I don't want. Right now, I can simplify the radical in the denominator because I can write it as the square root of 2 squared. Well, the square root of 2 squared is 2, and therefore no more radical in the denominator. Okay? I'm good with all my rules. That problem worked out really well because it was a perfect square in the denominator already. So what happens when it's not a perfect square? Well, then we have to force it to be a perfect square. So let's go ahead and break the square root of 5/6 up. The square root of 5 all over the square root of 6. Because the square root of 6 can't be simplified, the thing that I can do to get rid of this square root of 6 is multiply by the square root of 6. And then that would give me the square root of 6 squared, and then a 6 would pop out. Okay. So what I do to the denominator, I have to do to the numerator. So now I have the square root of 30 all over the square root of 6 squared. And I can simplify it now to the square root of 30 all over 6. When it is not a perfect square, the kind of easiest step to do is just multiply it by itself. But sometimes you don't have to take it that far. Let's say this was an 8. Then we're looking at 8 will be 2 square roots of 2. I would only need to multiply it by the square root, not the 2. You could, but then you would reduce later more so than you normally would. But I only have to get rid of the radical 2, so I only have to multiply it by the square root of 2 to get rid of it. So let's take a couple more examples, and I'm just going to go through these relatively quickly. I do have a radical in the denominator, so I need to get rid of that. Because the square root of 3 is not a perfect square, I'm going to multiply both the denominator and the numerator with square root of 3. Because square root of 3 over square root of 3 is just a 1, and I can multiply by a 1 all I want. 4 times square root of 3 is 4 square roots of 3. Square root of 3 times square root of 3 is square root of 3 squared, and therefore 4 square root of 3 simplifies to over 3. Let's try another one, a little bit more complex. 3 times square root of 3x all over the square root of 5y. 5 is not a perfect square, nor is the y, so I can't simplify it. So what I'm going to do is multiply both top and bottom by the square root of 5y. Square root of 5y. That, in essence, is multiplying it by 1, completely allowed. 2 times the square root of 3x times 5y is going to be, let me go ahead and write that step out, times the square root of 5y, all over the square root of 5y squared. That will give me 2. 3 times 5 is 15, x times y is xy, and the square root of 5y squared is 5y. It's a weird looking one there. Okay. Each of those examples, all I had to do is multiply it by what was already in the denominator, and then it just pops out. Okay. What happens when it is 7 over the cubed root of 4? Well, the cubed root of 4, I can write it as the cubed root of 2 squared. I'm looking for a 3 here. If I have a 3 as a power, it will pop out, because the cube root of a third power is that base. So how many cube roots of 2 do I need? I need one more, because I already have 2. So if I multiply both top and bottom by the cubed root of 2, not 2 squared, because that would give me 2 squared, and 2 squared is 2 to the 4th. I'm looking for 3, so I only need one more 2. What I do to the denominator, I do to the numerator. Therefore, that's going to be 7 cubed root of 2 all over the cubed root of 2 cubed, which pops out as 7 times the cube root of 2 all over 2. If I would have multiplied it by just the 2 squared or just 4, that wouldn't have been enough. I would have to do another time and another time. So gotta have to be a little aware of what your index is, and whatever your index is, that's what you want the power to be on the inside. For this example, I had a power of 2. I needed one more 2, 2 to the first, because 2 plus 1 equals 3, then it will pop out. Alright, the square root of 12x to the 5th y cubed all over 5z. First things first, let's break it apart. I only need to rationalize the denominator. I don't need to rationalize the numerator. So I do need to rationalize that square root of 5z. But there is a slight issue here. The numerator can be simplified, right? The whole goal is to get it in simplified form. So we've got to follow those 3 rules. First thing, can I simplify that numerator? Yes, I can. So first step, simplify the numerator. 12 can be written as 2 squared times 3, x to the 4th times x, y squared times y. Remember, I'm looking for, in essence, this index is a 2. I'm looking for things that are 2, 4, 6, 8, 10, 12. Those are the powers I'm looking for. For every 2, one of them will pop out. So a 2 will pop out. X to the 4th, well, that's x will pop out, as well as another x will pop out. That's x squared. Y squared, that will pop out as y, leaving 3x and y behind. Right? We want to practice that, and we'll have a few examples of that coming up. Now that we simplified the numerator, we're going to rationalize the denominator. So here's what it looks like now. 2x squared y times the square root of 3xy all over the square root of 5z. Let's rationalize the denominator. Therefore, I'm going to multiply both the numerator and the denominator by the square root of 5z. That will give us, the 5z will pop out, 3 times 5 is 15, x times y times z is xyz, all over 5z. And of course, the 2x squared y, that's coming along for the ride. Right? I do want to look that did multiplying by the square root of 5z, did it cause the numerator to not be simplified? And in this case, it didn't. 3 and 5s are both prime, so I can't break down that 15, and all of the powers on x, y, z are all 1, so I'm good there. But you always do want to kind of go back and look to see, do I need to simplify the numerator one more time? Let's work through another example here. The square root is 75 x cubed y squared all over 2z. Let's break it apart to where I have a radical in the numerator, radical in the denominator. First step, can I simplify the numerator? And indeed I can. So simplifying the numerator will end up with 75 can be broken down into 5 squared times 3. X cubed can be broken down into x squared times x. Y squared is just y squared. Anything with a 2 power can be brought out of the radical. 5 squared is 5. The square root of x squared is x, and the square root of y squared is y. Okay. Now, I'm going to carry that mistake all the way through. Sorry about that. All right. Now we can rationalize the denominator. Since 2z, we're doing the square root of 2z, I only need to multiply it by the square root of 2z, both on the numerator and denominator, to get rid of the square root of 2z on the denominator. By doing that, it's going to be 5xz times the square root of 3 times 2 is 6, and the square root of x times z is xz, all over 2z. There is nothing here we can reduce. There's nothing here that can be simplified. Therefore, we're done. Up to this point, we have always assumed that our variables were non-negative, but that's not always the case. Sometimes our variables can be negative. So let's talk about the square root of a perfect square. And let's consider the square root of 3 squared. Well, 3 squared is 9, and therefore the square root of 9 is 3. Likewise, the square root of negative 3 squared, well, negative 3 squared is 9, therefore the square root of 9 is still 3. Both expressions simplify to 3. We can also consider what is the absolute value of 3. Well, the absolute value of 3 is 3, and the absolute value of negative 3 is 3. We're going to use this fact to force our variables that come out of the radicals to be positive. Here's property 3 for radicals. If a is a real number, that means it could be positive, it could be negative, then the square root of a squared will be the absolute value of a. We're forcing it to be positive because we don't know if it's negative or positive anymore. Now, that's because we don't know. If we do know that it's positive, then the square root of a squared will just be a. Likewise, if we know that it's negative, then the square root of a squared, if we know a is negative, then that means that we have to take the absolute value of a, right? We're forcing it to be positive. And therefore, if we just don't know if it's negative or positive, then the square root of a squared is the square root of the absolute value of a, right? So that's generally what we're going to do, is when it comes out of the radical, we're going to put the absolute value markers on it to force it to be positive. Okay, let's simplify some radical expressions, and we are not going to assume that the variables are non-negative. So do not assume that the variables are non-negative. All right, let's simplify. The square root of 9x squared will be equal to, well, that is the square root of 3x squared. Therefore, that's 3, but we can't assume that that x is positive, so we must force it to be positive. The 3 is already positive, so we don't need that in the absolute value markers, just the variables. Okay, let's try another one. Well, the square root of x cubed will be the square root of x squared times x. Therefore, it's going to be the absolute value of x times the square root of x. Okay. Again, we cannot assume that that x was positive, so we need to force it to be positive. Okay. The square root of x squared minus 6x plus 9. It doesn't look like we can do much here yet, but let's factor. That's going to be x minus 3x minus 3. In other words, that's going to be x minus 3 squared, and we can certainly simplify the square root of x minus 3 squared as in the absolute value of x minus 3 absolute value, right? Into absolute value. And why is the 3 involved there? Because it went along with the x. So the whole thing has to go in the absolute value markers. Let's take the square root of x cubed minus 5x squared. The first thing we want to do is factor it and see if anything can be simplified. I can factor an x squared, leaving x minus 5. And then I can simplify, bringing out the x, but again, I don't know if that x is positive or negative, so I am going to put the absolute value markers around it. X minus 5 times the square root of x minus 5. All right, let's try a similar one, a little more complex looking, but the first things we want to do is factor. Right? Looks like I can pull out a 9 as the GCF as well as an a squared, leaving behind a squared plus 2a plus 1. Okay. But it doesn't look like I'm done factoring. So let's say that this is the square root of 9a squared, and a squared plus 2a plus 1 can be factored as a plus 1, a plus 1. But we can write this as a perfect square equals 9a squared, a plus 1 squared. 9 can be written as a perfect square. That it will be 3 squared, a plus 1 squared. Using my exponential rules, that will be the square root of 3a, a plus 1, all squared. Okay. You didn't have to. You could do it step by step here and keep bringing things out, but I'm just going to do it all in one fell swoop. Now that I have 3a times a plus 1 all squared, that is going to be 3 with the absolute value on anything that holds a variable, a plus 1 absolute value. The 3 is already forced positive, so you don't need the absolute value or absolute value around the 3, but you do need it with anything else that has variables. I do want to state one thing that sometimes trips people up, and it's the square root of a plus b. That does not equal the square root of a plus the square root of b. And I'm just going to give an example that describes why this is. Okay, I'm just going to say the square root of 9 plus 16, and that does not equal the square root of 9 plus the square root of 16. Well, 9 plus 16 is 25, so the square root of 5 does not equal square root of 9 plus the square root of 16. Square root of 5 is, or square root of 25 is 5, square root of 9 is 3, and the square root of 16 is 4. Therefore, 9 does not equal 7. Right? That's just, it's not proof that this holds up for every number, it's just an example of how it fails. So don't get trapped up into, if you see the square root of a plus b, do not break it up in the square root of a plus the square root of b. Okay. Now just as a reminder, when you have odd roots, it's okay to have negative numbers. For example, the cube root of negative 2 cubed, well, negative 2 cubed is negative 8, and the cube root of negative 8 is negative 2. Okay. Likewise with the cube root of negative 5 cubed, well, negative 5 cubed is negative 25, and the cube root of negative 25 is negative 5. So using those examples, we can extend property 3 for the radicals. If a is a real number, then the nth root of a to the n will be the absolute value of a if n is even. The nth root of a to the n will be a if n is odd. Okay? It's okay to have negatives when n is odd, so we don't need the absolute value markers around the variable if it's an odd root. And I will say the next few minutes of the lecture are a little bit difficult to understand, but it really is just visualizing roots of integers. And there's something called the spiral of roots. And how we build the spiral of roots is we take a triangle with the base of 1 and the height of 1. Connecting those, we get the hypotenuse of x. Using the Pythagorean theorem, we solve for x. X will equal the square root of 1 squared plus 1 squared. Therefore, x will equal the square root of 2. Now, from that first triangle, we can build more triangles. What we do, off the hypotenuse, we create another 90-degree angle with the length of 1. Okay, this happens to be 1 inch, 1 inch, 1 inch. And then we connect those again to build a second triangle. So it will have the height of square root of 2, the base of 1. If you want to see it turned around, kind of here's the triangle. Right? There's the triangle. So the hypotenuse is x. So x equals the square root of 1 squared times the square root of 2 squared, or vice versa. So x will equal the square root of 3. And we can continue this process. Off of the hypotenuse, we create a 90-degree angle with the length of 1. Connect. And that's going to be the square root of 3 squared plus 1 squared. Well, that's the square root of 4. And every time we do this, it's going to be the square root of 5, square root of 6, square root of 7. Right? That's how we visualize it. And let me see if I can find my picture that I created a while ago. Hold on. Okay, I said hold on in terms of, hey, I'll just pause. So here's I made a spiral of roots, and I took it all the way up to square root of 13. So 1 and 1, square root of 2. Square root of 2 and 1, square root of 3. Square root of 3 and 1, square root of 4. Square root of 4 and 1, square root of 5. Length of the square root of 2, length of the square root of 3, square root of 4, square root of 5, square root of 6, 7, 8, 9. And if you measure, this is 3 inches, 2 inches, 1 inch. Okay? And it keeps growing. It makes this beautiful shape, this spiral that comes down. It's almost like a nautilus. It's so beautiful. I find there are certain things in math that are just absolutely beautiful, and the spiral of roots, kind of one of them. Very beautiful. Now, we can't go around just drawing the spiral of roots, but what if I wanted to know the 10th diagonal, the length of the 10th diagonal or the 100th diagonal. What would I want? I would want to know what the length of it is, and I can write it out as a function. Right? This function is nice because we start off and it's the square root. The first diagonal is the square root of 1 squared times 1 squared, which is 2 squared. From that answer, we put it back into our function, and we get 3 squared. We take that answer, put it back into our function, we get our answer. We put it back into our function, and we get our fourth diagonal. So we can write it as a function. Our function notation is f of x will equal the square root of x squared plus 1. And we have to be given the first diagonal, f of 1. We plug in 1, we get the square root of 1 squared plus 1, that equals 2. The next diagonal is going to be the composition of the function with itself. Okay? So it's the function of function, the composite of function at f of 1. So f of 1, it's hard to say, giving us f of the square root of 2, because we're putting in the answer there. Then we get the answer of 3, the square root of 3. So the next diagonal will be the function of the function of the function of 1. In other words, it's the function of square root of 2 inserted in. The f of square root of 2 is the square root of 3, so it's a function of square root of 3, giving us the function of square root of 4. Now this continues on and on and on and on. Okay. So if the process that we're finding the diagonals, we can find it for any diagonal. The first diagonal is f of 1. The second diagonal is f of 1. Third diagonal is f of 1, and it continues, where f of x is the square root of x squared plus 1. Now your function might not always be the square root of x squared plus 1. So let's look at one that isn't quite that neat. Okay. Let's find the first terms if f of x equals the square root of x squared plus 4. And then we're going to predict the 10th and 100th terms. Well, first things we want to do, and we are given f of 2 to start off with. We plug into wherever there is an x, giving us the square root of 2 squared plus 4, in other words, the square root of 8. And I'm going to leave it like that. The second one is going to be the function of the function at 2. Well, the function at 2 was 8, square root of 8, so therefore it's the function at square root of 8. So we plug square root of 8 wherever we see an x. The square root of 8 squared plus 4 is the square root of 12. We bring this square root of 12 into the next one. So it is the function at square root of 12. The square root of 12 squared is 12, plus 14 is square root of 16. Yes, I know that's 4, but let's leave it as the square root of 16. And let's continue. The 4th term, we plug in the square root of 16. Square root of 16 squared is 16 plus 4. That is 20. The square root of 20. 5th, let's plug in the square root of 20. Square root of 20 squared is 20 plus 4 is 24. And the 6th term is square root of 24 plus 4 is 24 plus 4 is the square root of 28. Now what's the pattern here? Because we found the first 6 terms, let's predict the 10th and 100th. Well, if I look at the square root of 8, I can write it as 4 times 2. The square root of 12, I can write as 4 times 3. Square root of 16, I can write that 16 as 4 times 4. Square root of 20, well 20 I can write as 4 times 5. 24 I can write as 4 times 6. and 28 I can write as 4 times 7. So the sixth term is the square root of 4 times 7. Therefore, the 10th root, the 10th term, is going to be 4 times 11. In other words, the square root of 44 will be our 10th term. And our 100th term will be 4 times 1 more than 100, which is 101. And 4 times 101 is 404. Therefore, our 100th term will be the square root of 404. I know that was a lot, but that is it for this lecture. Until next time, be seeing you.